Today, we're going to talk about one of the most important stories of the modern age, and that's the invention of the microchip. I mean, it's a revolution that started smaller than your fingernail, and now it basically runs the entire planet.
And when I say our world is built on a grain of sand, I mean that literally. It's not a metaphor. The key ingredient for all this technology is silicon, which is, just purified sand. So how on earth did we turn something so common into the engine of the 21st century? Well, it all started with building a better switch.
And here it is. I know, it might look like a piece of lab scrap, right? A messy little bundle of wires and clips. But what you're looking at is quite possibly the single most important invention of the 20th century. This is the very first point contact transistor, built at Bell Labs way back in 1947. And this was the seed from which everything else grew.
So this tiny, solid little gadget replaced something much bigger, much clunkier, and way less reliable. To really appreciate why the transistor was such a game changer, we first need to look at the fragile, glowing glass bulbs that it made totally obsolete.
You see, electronics in the first half of the century all ran on vacuum tubes. They were basically these little glass light bulbs that controlled electricity, and honestly, they were terrible. They were big, they were fragile, they got incredibly hot, and they burned out constantly. Just to give you an idea, the first big electronic computer, ENIAC, had almost 18,000 of them, and it was always breaking down. The transistor changed all of that. It did the same job, but it was tiny, it was solid, it ran cool, and it was super reliable. This wasn't just a better switch, it was the key that unlocked portable electronics for the very first time. And these are the three guys who made it all happen: John Bardeen, Walter Brayton, and William Shockley. Their work at Bell Labs was so fundamental, so important, it won them the Nobel Prize in 1956. They had invented the perfect building block for the digital age. But it turns out that would soon create a brand new problem of its own. So here was the new problem. The transistors were amazing, but if you wanted to build anything complex, you had to painstakingly wire thousands, or even tens of thousands, of them together by hand. It was becoming a complete nightmare of complexity, a problem engineers at the time actually called the tyranny of numbers. A new, really radical idea was needed. And that radical idea was the integrated circuit. The thinking went something like this. What if, instead of making all these individual components and then wiring them all together, you could just build the entire circuit, the transistors, the resistors, all the connections, all at once on a single tiny piece of material? Now, here's the crazy part. Two different people had this brilliant idea at almost the exact same time, and they had no idea the other existed. Over on the left, you see Jack Kilby's version from 1958. It's a rough-looking thing made of germanium with wires kind of glued on. It proved the idea could work. But on the right is Robert Noyce's silicon chip from 1960. While Kilby showed it was possible, Noyce's design, now that was the elegant solution that could actually be mass-produced. And you gotta love this little story about how it happened. Jack Kilby was the new guy at Texas Instruments, so he didn't have any vacation time saved up. So while the entire lab shut down for a mandatory summer break, he was just left all alone to tinker with his crazy idea. And when his colleagues came back, yep, he showed them the future. So the integrated circuit was born. But what happened next was, in a way, even more incredible. You see, the pace of improvement wasn't just steady, it was exponential. And it was all guided by a simple but incredibly powerful observation that would become the engine for the entire industry. This is the famous prediction from Gordon Moore, one of the co-founders of Intel. Back in 1965, he just noticed a pattern. He saw that the number of components that engineers could cram onto a single chip was basically doubling on a regular schedule, about every 18 months or so. So he predicted it would keep going. And that prediction became a self-fulfilling prophecy. It became a target that the entire tech world aimed for. And check this out. This is the actual graph from his 1965 paper. You can see it right there. All he was really doing was connecting the dots from 1959 to 1965. But in doing so, he basically drew a roadmap for the next half-century of technological progress. It's amazing. So what did this exponential growth actually look like? Well, the impact was just staggering. In just a few decades, we leaped from putting maybe a few dozen components on a chip to cramming in billions. Each one of these steps, from small-scale to ultra-large-scale integration, wasn't just some technical milestone. It unlocked completely new things that technology could do for us. This is Moore's Law in action. But how? How did they keep doing it? I mean, how do you keep doubling the number of components on something that's already microscopic? The answer sounds almost comically simple, but it is one of the greatest engineering challenges in human history. You just make everything smaller. So let's try to put a number on it, just to really grasp the scale we're talking about. By 2010, a pretty typical feature size on a cutting-edge chip was 32 nanometers. Now, a nanometer is a billionth of a meter. That number is so small, our brains can't really comprehend it on its own.
So let's try an analogy. Picture a single strand of human hair. Its width is about 80,000 nanometers, okay? This means you could fit over 2,000 of these 32 nanometer features side by side right across the width of that one single hair. That is the unbelievable, absolutely mind-bending scale of miniaturization that we're talking about. For decades, the entire multi-trillion-dollar semiconductor industry has really just followed two basic rules to keep Moore's Law going. Rule 1, relentlessly shrink the size of the transistors and the little wires connecting them. And Rule 2, make the silicon wafers, that's the canvas you're building on, bigger and bigger. That's it. Shrink the parts and grow the canvas. That simple, two-part recipe fueled a technological and economic engine that completely reshaped our world.
So we've gone on this journey from a clunky experiment in a lab to a law of exponential progress that literally defined our modern world. But that law, it's hitting a wall now. The wall of physics itself. We're getting down to the size of individual atoms, and you just can't shrink things forever. And that leaves us with the biggest question in all of technology today. After 50 years of this relentless, predictable progress, what on earth comes next?